Now, methods of undetermined coefficients are not always possible. See, because methods of undetermined coefficients need to include all the derivatives of the right side, if the right side has a derivative which doesn't end, if it just produces endless linearly independent functions, then you can't use the method of undetermined coefficients. For example, tangent x, if you differentiate this, you get secant squared. If you differentiate secant squared, you'll be getting 2 times secant squared tangent. And then you keep differentiating, you're going to get a bunch of more and more complex functions. And you can try out by Wronskian or some method that all these functions that you create when you differentiate will all be linearly independent. They're all linearly independent. So that means if you have such an equation, you need to do something totally different. You need to find a totally different way of solving this. And for some very specific cases, you can find the solution by using something called variation of parameters. Variation of parameters. Now, sometimes variation of parameters will give you the correct answer, exact answer. Sometimes it may not, but always you'll find that the variation of parameters can give you the answer in the form of some integral. The problem is, in many cases, the integral will be some kind of integral where you can't calculate. Okay? This one, you'll see that you can calculate the integral. Okay? All right, so what is the variation of parameters? Let me try to explain it by using this example. All right, so the first thing you do is you start by complementary, just like before. So r squared plus 1 equal to 0. That's your characteristic equation for the complementary solution, right? And if you move the 1 to the other side, and you take the square root, which is plus minus of I, then you see that your yc is c1 times cosine of x plus c2 times sine of x. Okay. The reason that you get this is just think about this as 0 plus 1i. You know, in general, if your solution looks like a plus minus bi, your complementary solution should look like e to the ax times cosine bx, and another one will be e to the ax sine bx, right? So these should be the two solutions coming from the solution of the characteristic equation. And here, it's the case where a is 0 and b is 1. So e to the 0th power just gives you 1, and you just get cosine of x and sine of x. Or you could have figured this out just by investigating the left side. I mean, what's the complementary solution? Complementary solution is the solution of y double prime plus y equal to 0. That's the complementary equation for this non-homogeneous equation, right? And that one has a simple solution. If you differentiate cosine twice, add to the original cosine, you do get 0. So you can easily check that these are indeed solutions. Okay? So that much is exactly the same as what you would do for a method of undetermined coefficients. Now here is where this different idea comes from. The method's name is variation of parameters. What are parameters here? The parameters are C1 and C2, right? These are the parameters. And the idea is you kind of, after a lot of experience in handling differential equations, you kind of have the idea that a lot of times your particular solution may look like some function times cosine x and another function times sine x. So what you're doing is you're replacing the parameter by a function. C1 is replaced by a function. C2 is replaced by a function. Okay. And because you're replacing a parameter by a function which varies with respect to x, right? C1 is what? It's a constant, so it doesn't vary with respect to x. But now U1x, that varies with respect to x. So that's where this name variation of parameters comes from. Okay? You're replacing the constant by something that varies, another function. Okay. All right. Now, so if you think that this is the form of the answer and you want to find out U1 and U2, what should you do? You differentiate once and twice, plug it into the left side, and set it equal to the right side, and you figure out what U1 and U2 are. That's what you would get. Okay? All good? All right. Now, however, there's a problem. See, if you differentiate this twice, and you plug in everything to the left side and set it equal to the right side, you just get a single equation, right? But how many unknown functions are there? 2 unknown functions and only one single equation. And that's not good. So that's why you need to have one more assumption about these functions. Yeah. And these assumptions are very ingenious. I mean, unless you had a lot of experience about these differential equations, you wouldn't know that this could be a solution, nor you would know this the next condition that we are about to impose. Okay, let me show you the next condition, yp prime. If you differentiate this, you get u1x, differentiate the cosine negative sine x, right? Because you have to use the product rule, that's what's going to be created. Plus, the other form is you differentiate the first one times the second function, right? And then if you differentiate this one using the product rule, you would get u2 times derivative of the second, which is cosine x. And then you differentiate it plus, you differentiate the first one instead, and you get u2 prime sine x. Okay? So I just used the product rule to differentiate both, except I organized it so that the ones with u1 primes and u2 primes will be here. Okay? And the assumption, the extra assumption is that the terms with u1 and u2 primes, sorry, I forgot an x here, u2 prime x. The extra assumption is that the terms with u1 prime and u2 primes will equal to 0. Okay? And it's okay to assume this because this will give you one equation for the 2 unknown functions u1 and u2. And then when you differentiate this again and you plug into the left side, that's going to give you a second equation for u1 and u2. And therefore, you have 2 equations for the 2 unknown functions, and everything's good. Okay? All right. And it still makes you wonder, I mean, after that, how would you know that you would get a solution? Well, you know, again, the deal is we're really not solving the equation. We're just guessing, making wild guesses, or educated guesses. And therefore, if we assume so many different things, and somehow at the end of the day, if we created the solution, then that's it. Yeah, the end justifies the means in our case, okay? Because we're just guessing our solution. So we're just coming up with these seemingly plausible conditions, and at the end of the day, we just hope that it will create the correct solution. Okay. All right. So let's continue on. So remember, this is our first condition. Now let's differentiate this. This is yp double prime, and again we have to use the product rule. The product rule will give you u1x times negative cosine x, okay, plus, if you differentiate the first one instead, I'll get u1 prime of x times negative sine x. And then plus, yeah, it's always a good idea to split the product rule into 2 parts. and distinguish the ones with u prime and ones without the u prime. This one, u2x negative sine x, because if you differentiate cosine, you get negative sine. And then if you differentiate u2 by itself, you get u2 prime of x cosine x. Okay, now we plug everything into the left side. Okay, I'm going to erase the complementary. Don't forget what the complementary form was. It was just c1 times cosine and c2 times sine. All right. So now we plug everything to the left side. There's no need for y prime because there's no y prime here. Yes?
Would the u prime x and the u2 prime x on the double prime also be equal to 0?
No. Then we can't, because now if you also impose this to be 0, then you would be getting 3 equations for the 2 unknowns. Then that's too much. See, whenever you try to solve an equation, you just want to know, have the same amount of unknowns as the equations. If you have too many equations for the unknowns, you say this is an overdetermined system, which means sometimes those kind of systems won't have solutions at all. If you have too little equation for the amount of unknowns, then you have an underdetermined system, which means you can't figure out what these are. You need more information. All right, so now we plug everything to the left side. I see that this is not needed, but we need this one and that one, right? So let's see what you get. What do you get if you do yp double prime plus yp? So I plug these into here. This yp double prime is, I'm getting lazy. Let's just look at and see if there's anything that cancels. There should be something canceling. What cancels? Yp and y double prime. Add them up. u1 cosine x, u1 negative cosine, these are negatives of each other, so if you add them, it's going to cancel, right?
Say u2.
And
u2 sine x, this one will also cancel, right? So what's left after canceling?
Just the primes.
u1 prime of x, negative sine x, plus u2 prime of x, cosine x. Okay. That's what's left after canceling everything. And as you can see, the only survivors after doing all the calculation are the ones with u primes, right? And if that happens, that means you're on the right track, okay? If for some reason you computed everything and you still had u1x without the primes and u2x without the primes, if those appear, that means you made some mistake in your calculation, okay? If you did it correctly, always the survivors will be only the ones with u prime, u1 prime and u2 prime, okay? All right, so that's what you get if you plug all these into the left side. What should this equal to?
Tangent x.
Tangent x. This should equal to tangent x. Because that's on the right side. Okay? And then we have this condition too, u1 prime x cosine of x plus u2 prime x of sine of x equal to 0. And I don't want to erase the yp itself, because at the end of the day, after we figure out what u1 and u2 are, we have to replace these to get the particulars here, right? Okay. So we have u1 prime and u2 prime. These are the two things that we don't know. And we have two equations. How do we solve? Well, I guess,
Wait, what?
yes. You have a question?
Yeah, what's the second line?
This second line?
Yeah.
This came from this additional assumption that we did. When we differentiated this, there was some u1 prime and u2 prime that was created, right?
Okay.
Yeah. And we said I want that to be equal to 0, right? Because if I set that equal to 0,
Yeah, the first one.
then the calculation afterwards If I don't have that as 0, then y double prime p will be very messy. But if I have that as 0, then y double prime of p is somewhat manageable.
Okay.
I think the original people who invented this method had the assumption just so that y double prime p will be easy. Yes?
Never mind.
Okay. So you should solve this. How do we solve this? Okay, there's the straightforward method where you solve for one variable, one function, plug into the next equation, and then solve. So that's that. Should I do it that way?
I mean, if you did that, you get
U1.
10.
Yeah, let's do it. Let's do it. I think I want to do the following. I want to solve for U1 prime. So I move this to the other side. So you get negative U2 prime of x sine x. And then divide both sides by cosine x. Which now means that U1 prime is this much, right? That means I can now plug this into this top.
What about the x? Should it still be u1 prime of x?
Oh, U1x, U1 prime of x is this thing, okay? All right, so now I can replace the U1 prime of x as this thing, which is,
Did you just say that's tangent?
Yes.
Sine over cosine?
oh yeah, it is. It is
Yeah.
tangent.
But
You know, let's do it this way. Let's just make the tangent as sine over cosine, because then I can just multiply cosine both sides. I like that better, okay? So let's plug this in here, and you would get u prime of x times what? U1 prime should be replaced by minus u2 prime of x over cosine of x, sine x. And then there's this negative sine x there, so I put that there. And then plus u2 prime of x cosine x. I'm suffering lack of spacing. u2 prime of x cosine x.
Would it be so for you too? 'Cause I'm gonna cosine
And
over
that's
sine.
equal to sine x
No,
over
that wouldn't
cosine.
matter.
Yeah, it would have the same
We
problem.
got the same problem.
Okay? Now multiply cosine everywhere. What do you get? Unfortunately, I think I need to erase this one. I don't have room. So first, if I multiply the cosine x, these cosines will go away, but this one will be squared, right? And then negative negative becomes positive. So here's what we get: u2 prime of x sine squared of x plus u2 prime of x cosine squared of x equal to sine x. Right? After
You times it all by.
cosine. Everything multiplied by cosine will get rid of the cosines, but this one, which only had just one single cosine, will become now cosine squared. So that's what I got.
Isn't the U2 negative?
No, there's two negatives. Negative of negatives.
Oh.
Yeah, so there's a negative from here and another negative from here. All right, now sine squared plus cosine squared, what's that?
1.
1. So what do you get on the left side?
Wait, what happened to the negative?
Oh, isn't this nice? Right? Yes.
Oh, what did we do with the negative? There was negative u2
Yeah,
prime?
so here's a negative
Times
here.
negative sine x.
Here's another negative
okay,
here.
yep.
If you multiply the two negatives, it becomes positive. So we got u2 prime of x as sine x. Once you get that, now you can replace this u2 over here to get u1 prime of x as negative sine squared over cosine x. Okay. So did we find u1 and u2?
Yes.
Did we find u1 and u2?
Not yet, not yet.
Not yet, why not?
No,
U1
we found
prime,
prime.
you look for U1.
So what's u2?
The integral of that?
Or you have to integrate her. Okay. What about this one? Oh, that's a little hard to integrate. Let's see. Oh, you know what? This is same as negative sine squared is same as cosine squared minus 1. Okay? Because sine squared is 1 minus cosine squared. Everyone knows that, right? Sine squared is 1 minus cosine squared. And cosine squared is 1 minus sine squared. They all come from the fact that sine squared plus cosine squared is 1. Okay, so you should know that. So this is what you get. And then that's equal to cosine squared over cosine is cosine. And 1 over cosine is secant of x. Okay? So that's u1 prime. So what does that mean for u1 prime? U1 itself. Integral of cosine is sine. And integral of secant x is, I doubt anyone remembers this, but it's 1/2 ln of the absolute value of secant of x plus tangent x. Okay? This is something that you did in Calc 2. Okay? Okay, that was a whole lot of mess, but after long and hard work, we found the solution, which is, the solution is yp, u1 is sine x minus 1/2 ln of secant of x plus tangent of x times cosine x plus, so this is u1 times cosine x, and u2 is negative cosine x times sine x. Oh, and this is just a pure coincidence. Somehow if you multiply sine x times cosine x, you see that this is cosine x, negative of cosine x times sine x. So at the end of the day, you see that these two cancel, and the simplified version is negative 1/2 ln secant of x plus tangent of x cosine x. And now what's the final answer? What's the general solution? YG is YC plus YP, which was C1 cosine x plus C2 sine x. That was YC, right? And then your YP is this thing, so it's minus 1/2 ln secant of x plus tangent of x times cosine x. So that's the final answer. Okay. All right, so what you're seeing is that compared to method of undetermined coefficients, how is this? Much harder, right? But on the bright side, it was able to give us a solution of what? An equation, a non-homogeneous equation, which was impossible to be tackled by methods of undetermined coefficients. Okay, so that's the good side. Okay, I mean, another way to view it is this: you have a seemingly easy question, which is actually pretty hard. Yeah, tangent x, to get that's really hard. I mean, look at this. If you were just trying to guess the particular solution just by pure luck, would you be able to think about this? This will be really, really hard, right? So, I mean, although it was very long and hard, it really was worth it. This is how you get the answer.